This is now lecture 6 or chapter 6, elements of models, in the course or the module models in sciences, especially models in modeling in computer science. This is now the starting part of the second part of the lecture. We consider in the second part elements of models, deep and normal models, conceptualization and conceptual models, model suites, and stereotyping of models or stereotypes of models. In chapter 6 we will cover the construction of models, the tricks of construction, generic models, and stereotypes. The ingredients for a model being are essentially: a model is an instrument that somehow functions in scenarios, is based or reflecting origins, has a background consisting of the grounding and the basis, is set into a context, and is somehow used by a community of practice, developed, and in general understood. Of course, a model should be adequate and dependable. For this reason, we come up now with a relational structure consisting of the 9 tuple, but it answers mainly the question how, wherefore, and wherewith models are used. Currently, we can distinguish a good number of very different models, and this number of models consists, for instance, or this kind of models consists of situation models reflecting a given state of affairs, especially domain situation models reflecting a given application in a proper way that is agreed within a community of practice, or perception models reflecting a personal current understanding of the world. We have formal models, like the typical ones are mathematical models. We have models that are enhanced by conceptions. We have also mathematical models, of course, in the language of mathematics, with all specifics mathematics says. And we have also representation models. Those are models that are used for the representation of, let's say, our thoughts, understanding, whatever we model. Typical representation models are visualization models. They use some visualization. We come in the second part of this chapter again back to visualization models. We will not consider in this chapter diagrammatic models. They use a specific language like we use in UML. And we will not cover some other kinds of models here in this chapter. But you see here you have a very good number of different models representing the modeling approach in a very different fashion. One of these kinds is, for instance, the kind of informative models. They provide an explanation, or let's say they inform us in a current way how we want to be informed, based on our information demand, based on our profile and portfolio, and based on our specific wishes to have an insight. Such kind of informative models are typically, for instance, enclosed labels, product inserts, or package inserts like we use in pharmacy, or instruction leaflets, or information and direction for users. They provide an information about the utilization scenario, about the methods provided with the model, about the cargo of the model, with the mission, determination, abstraction, declaration of the meaning and the identity, of the content of the model, and of course some kind of evaluation of the adequateness and dependability of a model. The content can be given in or evaluated by the strengths, weaknesses, opportunities, and threats, or it could also describe how simple, meaningful, adequate, realistic, and trackable is a model. It means you have a SWOT or a SMART evaluation. It provides information about how the model is used, or the model behind the informative model is used. What is the main background of the model behind the informative model? Why to use the model behind the informative model? That means the origin of this informative model. The informative model gives us therefore some knowledge or a number of facts or circumstances, how to use, how to apply this model, with an integration of the matter and the fact, with some substances, and in general it is somehow a specific kind of model that is especially oriented on the cargo of a model. This means it informs the potential user through bringing facts to somebody's attention, provide these facts in an appropriate form according to the information demand, guides them by steering and directing, and leads them by changing the information stage or their information stage and their information level. Typical characteristics of an informative model are objectivity, the functional information that is given, some kind of official maybe, certified information, some explanation, some description what will happen in the future if you use this kind of product described by this model. It gives a different representation media and presenters, has a different degree of extraction from open to hidden, and of course we can use a variety of styles to provide the content of such kind of models. A typical informative model can be representing, for instance, a conceptual database structure model in a description scenario. In this case, we are representing the database schema, we are representing the views, especially those coming from the business users, maybe the models behind we are using for the development of this entity relationship schema, and of course the declaration of model adequacy and dependability. And you see here that our 9 tuple boils down to a quintuple. In a prescription scenario, we have additionally some views, especially for system representing system operating. That means in this case we have an additional number of views beside what we have here for business users and beside the database schema. Typically we have also some kind of model directives for the implementation or realization of a model via system. That means we have some kind of maybe realization template we are using for describing what is used in this case in the prescription scenario. I will come back to this part again in the chapter 8 of this module. The entity relationship schema language has already been developed in the late 70s, and it was mainly oriented on documentation scenarios. And documentation scenarios, and the model had to describe what is the schema of a relational database specification. In this case, of course, you have also a number of views supporting business users and the system operating. So you have additionally maybe a collection of operating structures, and you might have also an interpretation of the notions used in the origin based maybe on some kind of codified concepts. That means in this case the documentation of an entity relationship schema is somehow given in a way, let's say in a graphical form or in diagrammatical form, or maybe also in some kind of form for this informative models. If you go now for the specification, you can use a number of tricks. Let us start with a pretty simple trick. There are a muscle of perspectives of the human perception. You perceive the environment, you perceive the behavior, you perceive the capabilities, You integrate them into beliefs and values. You have some identity, and anything in the world has some identity, for you at least. And representing something has somehow to satisfy a mission. It means you're asking questions like who, else, who, why, how, what, where is somehow representing the given perspective. That means in this case you have a rhetorical frame. The rhetorical frame leads us back to what I represented already, the Hermann of Temnos, who used the rhetorical frame for who, what, when, where, why, in what way, by what means, descriptions of a number of sentences or a rhetorical statement. So in this case we have some kind of maybe separation of the W-H specification frame. The central dimensions are purpose, origin, carrier, and added value. That means you're asking wherefore, whereof, wherewith, and for worthiness. One additional thing is here you ask for maybe a secondary characterization. The secondary characterization is something like you have a user and a community of practice that can be characterized. You have an application domain that can be characterized. You have a way how to characterize the solution. And maybe you have some additional context characteristics. And again, we can ask a number of W questions, starting with wherein, and finally maybe asking when. This specification frame is well known, and for this reason it is pretty interesting that we can embed this in the classical linguistic question word frame. The question words have functions. For instance, with a which question you ask about a choice. With a who question you ask what or which person or people are somehow involved in a certain activity or a structure. With a how question you ask about the manner, or you ask about the condition or the quality. It means in this case you have some kind of functions for the question words. You can structure it a little bit different using the meaning. Then you say, okay, fine, who, you're asking for person. Where, you're asking for a place. Why, you're asking for reason. When, you're asking for time. And finally, maybe you ask the how questions, how come, and you ask for a reason. And this specification framework can be now somehow a little bit more structured for our purposes into a specification of the concepts. You ask a wherefore question, you ask for the purpose. On the content, that means you ask for the supporting means, you ask wherewith, and you ask questions about the application domain. Third, you ask for somehow an annotation, maybe based on topic maps or something else. You ask for the sources, that means whereof, and you ask for the party and the activity. Or you ask for the added value, that means you have some kind of surplus value service name, and you ask for the worthiness and for the context. It's a pretty general specification frame, and for this reason it might be sufficient for our purposes to represent anything what is concerned with models. You can use, for instance, this kind of specification frame for the specification what is a service. You can say, okay, fine, a service is based on some basis and background. It uses methods, so from the sources and technology. It is supported by means for use. It has a surplus value in some application domain for certain activities. So that means you have a context, a community of practice, you have a portfolio and the purpose, and the model looks pretty similar, despite that you are using instead of the origin your description of the portfolio. You can separate service specification into a number of phases a service is used. Maybe you have a planning phase. The planning phase, of course, describes the full background. within the application and deployment scenarios. So the service should function in those. And of course you consider business rules and portfolio together with the goals, intention and the profile of the service. The second phase would be building the service. That means in this case you have to use, of course, methods and a part of the basis for building this service. And of course you consider again the application cases, and you consider the needs of the community of practice and of course the context. The next phase would be using the service. So in this case, of course, the grounding is not of interest. It is of interest to have a good number of methods for using it, for deployment and utilization methods. And of course, you want to have these methods to be somehow used by the community of practice. And you consider again the application cases and the functions in the application. That means in this case we have a general framework even for specifying something else beside the model build, but services could be also specified this way. So, and if you want to have a little bit more, let's say, evolution of a service, then in this case you don't consider anymore as a background, you consider only the methods to support somehow the evolution of a service, maybe an adaptation to new circumstances, with a number of application cases, with some kind of function that can be used in order to be somehow in a proper or to represent the service for, let's say, the future circumstances. This leads us directly to some kind of specification separation based on 6 dimensions. Of course, finally, we arrive with the representation of models somehow, or maybe by a model suite. As I told you, the model suite will be covered a little bit later. One dimension is the community of practice, with the intention, the meaning, the demands of our members of the community of practice. Another one is the context or the disciplinary or the knowledge dimension. Another dimension is you consider, let's say, the initials, maybe based on generic or references or to somehow what has been already developed. And you really represent origins that are considered and targeted. You use some kind of methodology, or more generally, you use some kind of way of having or organizing this kind of methodology. That means you are using some kind of mold. And the 6th part is now you are using, in this case of course, tools and techniques. Tools, of course, also have their obstacles, their problems, and for this reason you have to accept those, as well as our molds, as well as our context, as well as our initials, as well as our community of practice. But with this separation of concern, it might be easier to specify what is in a model. We have 2 dimensions typically considered in sciences. That is maybe not the right thing. Most people say, okay, fine, models are representing maybe states of affairs, of phenomena, of situations, or models are representing representations of theories, and somewhere in between these two the model is used for representing state of affairs as well as the corresponding theories. However, you can use very different models representing the same state, very different models for representing the theory or some parts of the theory. That means in this case our, let's say, models might be somehow independent of, or partially independent of the state of affairs and of the theories. That means in this case we have to consider it in a different way. Let's go back for a proof by authority to the work written by Morrison Morgan, Models are partially independent of both theories and worlds we want to prove by the statements we have been making. The autonomy of a model, of models, due to their construction we have to consider. A model functions in various scenarios and comes in a variety of forms. Models for investigation represent either some aspect of the world or some aspect of our theories about the world, or both or at once. Learning from building the model and from manipulating it is one of the scenarios. And finally, maybe we arrive with learning might take place with the world of models. That means in this case we have a number of different ways how to characterize the usage of a model, and we see that models are really partially independent of both theories and the situations they represent. Okay, in this case we boil it down to models can be considered as a third dimension of science. In reality, we are representing state of affairs, our worlds, our theories, by models, by very different kinds of models. And in this case, we have maybe to consider the model as a very essential part of our disciplines that maybe represent our states of affairs and theories, and use models as an instrument for investigation, for consideration, for learning, etc. So in this case we arrive now with a different picture. Models are the third dimension of science. State of affairs are represented by models. Models are illustrated by situations. Theories are used for understanding, comprehending, are using models. And models used for the computation of meaning, of their understanding, theories. The classical separation of concern between theories and situations is, of course, explanation and exploration. This leads us also to another observation. Jim Gray has been writing a number of articles, papers about we have nowadays a fourth generation of sciences. In classics we have had the empirical sciences, describing natural phenomena, experimenting and something like that. We have theory or science-oriented sciences. They are based also on models and generalizations. We have numerical sciences or computational sciences, I would call it better, with simulating complex phenomena and computing some kind of behavior of these complex phenomena. And we have, of course, also data science that is using maybe experiments, unifies maybe some theories, but using data and simulating behavior of systems by such data. So that means in this case we arrive now with a little bit different observation. Models are used for visualization of phenomena, experiments and observations. Models are used for representation, for communication, understanding. Models are used as mediator or starting point, let's say in inverse modeling. Inverse modeling is nothing else as parameter adaptation of models, where you have a number of free parameters and a number of somehow parameters that are representing our observations and can be somehow used for specializing the model. And finally, you have also models as a starting point for hypothesis, investigation and pattern detection, like we do in data science, in data mining, in machine learning and other approaches. That means we have now models as the third dimension, and we have a number of different models depending on the generation of science. Of course, most sciences are somehow based on maybe 1, 2 or 3 or 4 generations. That means in this case our models can be seen for a third dimension of science. They provide a number of methods. Later when we come back to the model suite issues. That means we have a collection of associated, well associated maybe models even, in a variety of abstraction level, foci and scopes. We represent maybe also models by a number of models representing evolution of, let's say, a system, or used for migration to another system. We can use models as a means for experiments. And another thing is, of course, models can be used as a general model. They can be somehow specialized, refined to, let's say, parameters we can observe, to more special models. And in this case, we have maybe some a method that is called in geophysics or in physics in general inverse modeling as a stepwise refinement of models. Yeah, let's now talk about parameters. How to represent what are the essential elements of models. I would claim the first essential element of a model are variables. We have very different kinds of variables. Some variables might represent an evolution of a system. Maybe the evolution is not existing or not considered, then in this case we have a static variable or parameter, or it becomes dynamic. We can have also deterministic parameters or stochastic parameters. Parameters can represent the values by discretization using some kind of discrete parameter space and data space, or we can do it by continuous domains. A model can have parameters that are simple, basic, atomic, that means one-dimensional, or they can be complex and many-dimensional. Models might have parameters that are interdependent. Some of them are independent, others are correlated. That means in this case we should have a glimpse of how this correlation is working on our parameter space. That means in this case we might have a very large parameter space. In the sequel I will show you an example how large the parameter space could be and how we can reduce the dimensions in our parameter space. We have a number of problems as well with our parameter representation. First of all, some of the parameters might not be observable, or they might be observable only by secondary parameters. Think about the electrocardiogram. It is essentially a, let's say, phenotype observation, not a genotype based on the real parameters. It's only some kind of observations we are doing. Or we might have models in experiments. What is then the value of assigned to a parameter? Or we might have, let's say, models that are somehow doubtful, somehow too restricted, but somehow nice, like metaphors, or let's say the Bohr atom model. That is a great thing. It transforms our, let's say, origins, but have a limited validity. Or we might have prototype models which are based on the most essential elements of our origins for demonstration, for easy communication, but they have a very limited background. That means again our parameters that becomes a little bit more, let's say, problematic. We can also use methods for reduction of models. I will show you one method here where we are reducing our parameter set to kernel parameters, we call later order parameters, and let's say to side parameters that are in reality enslaved parameters. We might have also to consider in which cases this model should not be used. That means in this case we can have a restriction on our parameter space according to the purposes and the goals. And of course the community of practice strikes through. It is one of the directives of models. That means in this case a model and the parameter space is dependent because of the acceptance of theory, because of the theory-ledness of a model, because of the paradigm-ledness of a model, because of our perceptual experience, because of our modeling experience and knowledge, or the working methods or the work methods, and because of the limitations. Think, for instance, about the Sapir-Whorf problems in linguistics we have been covering in the 4th chapter of this module. And we have another, not less problematic part. Assignment of values to parameters means in this case we have also to handle errors. We can have, as an easy kind, stochastic errors. In this case we need nothing else as a distribution function, and then we can say, okay, fine, we have some kind of likelihood of a certain value assignment or a certain value for a certain parameter. More problematic are systematic errors we can make, maybe based on our abstraction, restrictions on the accessible data, dirty data, approximations, computations. A very bad part are systemic errors. That means we make mistakes because of the way how we are developing a model, how we are using a model, how the way how we understand our scenario, and for this reason our misunderstandings of the function. This error is pretty difficult to handle. Handling errors means in this case we have maybe methods for error prevention. We might have also, especially for the case of stochastic errors, probabilistic error models that allow us somehow to handle the errors, or we might have also error cleansing algorithms. That is the best. Typically, mathematical models are somehow mapping parameters that can be observed or that can be imagined for an environment to parameters and parameter values within this environment. That means we are using some kind of problem-oriented mathematical method that is, of course, based also on a solution faithfulness of the solution we develop with such models. We have maybe some description of coherence and correlation, maybe between the input states and the control states and the output states. In this case, we can have this general model somehow represented by a mathematical function that has a number of internal states, maybe a starting internal states, a number of parameters, let's say input parameters or control flow parameters that are somehow represented, can be computed, can be used for the computation of a function value for these parameters and a certain output vector. So it's a pretty nice way how we do it in mathematics. How we handle now parameters. That is now maybe a little bit more difficult part. Typically, our parameter handling is somehow having the problem of the complexity of our parameter space. Think, for instance, about performance models for, let's say, computing systems, like, for instance, the database system. You can represent the parameter set. You can use some kind of observations you can have under certain circumstances for these parameter sets. So it means in this case you have now a pretty complex parameter set. In the case of the Oracle database system, it is about 200 parameters you have to consider. The parameter visualization you can have now on your observations, a parameter observation, and you can put something for your walls, how the parameters are somehow related, let's say, to a time development or time series. In general, you have in this case, let's say, a database management system consisting of a number of databases. It has a portfolio that any database management system provides. That is based again on the profile of an operating system and of the hardware. And you have maybe your application with the task you have to solve somehow. That means you have a portfolio, and this should match to the profile of that database management system. What you do now for model development is nothing else as you try to monitor the parameters. You have some kind of capability for data analysis. You build models, you forecast, and maybe later you can also proactively tune the behavior system, or you can a little bit better manage the resources you have in the system. Okay, that looks like a complex task now. Let's look how it happens and how it goes. First of all, you record all parameters. Next, you try to reduce the dimensionality of your parameter space, maybe using some kind of regression approach. In regression approaches, you do nothing else as to state that a certain parameter can be somehow computed from other parameters. And then you can check whether this regression function is correct. In this case, you have maybe some deviations for the regression function, and then you observe how good are, let's say, is the system behaving, and how good your red part here is somehow representing the blue part. Okay, fine. In this case, we have an almost nice or perfect matching. Then you can develop a number of mathematical models. For instance, you can use Q theory. And in this case, you say, okay, fine, I have Q models in a different form. And finally, you can say, okay, fine, now I can reason on that. For instance, I can reason on the dependence of user calls, executes per second, and CPU parameters. And then I see maybe based on a week observation that on weekdays, for certain weekdays in the first week and for certain weekdays in the second week, I have a completely different behavior for each of the weekdays, for Mondays, Tuesdays, Wednesdays, and so on. That means in this case, maybe there is no regularity in the behavior. Maybe there is somehow a detectable regularity. That means in this case, the parameter space might become pretty complex. One approach for reducing complexity is synergetics. You say, okay, fine, I have maybe parameters that are very important, that are kernel parameters. Let's call them order parameters. They are enslaving the other parameters you can observe. And for this reason, you can say, okay, fine, if we have the order parameters, we have maybe a complex function for enslaving, but we can represent anything by order parameters. And if we can do it so, then we can say, okay, fine, then we can now apply control parameters for regulation of the order parameters. And then in this case, you have some kind of a picture here, like you have control parameters you are using for controlling. You have order parameters that are guilty for almost the full, let's say, model behavior you have for your application. And the enslaved parameters are somehow dependent on the rest. That means in this case, maybe you can also decompose the system. You have now some way how to reduce our parameter space in a proper form. That means in this case, you have order parameters as driving, maybe having some patternized behavior. Maybe they can be based on some kind of equational system. Maybe you can now use also timelines to observe what is the behavior over time. And then in this case, maybe you can use all the mathematical approaches you know, including, for instance, attractors. And you have, according to the slave principle, of course, parameters that are important at the microscopic level, but they can be somehow neglected using maybe some stochastic error treatment. And for this reason, they are not any more of importance. And then you can use the control parameters to regulate the system in a proper form so that the system is behaving relatively well according to the requirements you have been making for, let's say, a smooth behavior. You have, however, a little problem with measuring. Let's take it for a very simple example. Let's say a certain population is sick, a certain number of people are tested by a test that has maybe a certain correctness. Let's say you have 10% sickness, 10% tested people, and maybe 80% of correctness of the test. I should mention that this test with 80% is a pretty bad one, and I will show you why it is bad. If you go now from the first, let's say, the space here to the second space, you observe the colors are changing. What the colors are representing? The blue color represents correct testing. That means in this case, the test says for sick people, they are sick. The test is positive. You have a magenta part that is almost not visible here, becomes visible later. That says, okay, fine. You have maybe treated people. They are sick, but the test says negative. This is the so-called false negative test result. You might have also tests that are completely different, that say, okay, fine, people are sick, but they are not sick. I represent it here as a black part. These are the so-called false positive. And of course, you have a number of people who are sick and not tested. I represent those by the red part. The red, the black and the magenta part are showing us now the problem of having, let's say, a very low data precision. Go from 1080 to, by increasing the number of tested people, let's say to 50% tested people. In this case, our red increases and our black increases a lot. And magenta part, of course, is also there, but not really visible. If you go now from 50% tested people to 90% tested people, you see that the black part increases a lot. The red part, of course, is becoming smaller because of you have almost everybody tested. But the magenta part is now becoming visible a little bit better. So that means in this case you have now, if you go from the upper left to the lower left to the lower right, then you see that the test precision is really a problematic part. You can see the same if you go from left upper to right upper. Let's say you have more sick people. In this case, you have a good number of not tested people that are sick, and for this reason you have now a larger red part here in this. That means in this case data precision is a very essential part of, let's say, analyzing our parameter behavior. Okay, let's now go as the last part of the first part of this lecture to composition of models. Composition is based on a principle of abstraction and refinement. You have maybe a component abstraction. You might have also an abstraction from the context, and then you have to decontextualize again the developed model to, let's say, a model that is not that is more precise. You can have also a detail abstraction. Detail abstraction is typically based on information hiding in computer science. You abstract from the details and you say, fine, those are not interesting, or say those are enslaved parameters and I don't consider them, or I focus on details that are essential and I somehow neglect the other details. Abstraction and refinement are the opposite directions. You abstract to the more general one, you refine to the more special one. For component refinement, you have something like generalization, specialization hierarchies. You have maybe some grouping, we later call it class development. You might have also some aggregation, or let's say a decomposition as the opposite. That means in this case you are using some kind of principles, and the three principles for component refinement have been introduced by Smith. Okay, let's now look for context abstraction. Context abstraction is a little bit more, let's say, that is all, context is anything what is outside the in-text. That means you have some localization context. You might have also some temporal context. You might have also some story context. Some parts are important at a certain stage of the development of a story. Or you have some usage context. Or you might have a system context. So it means you have now a pretty different way how to see the essential components or elements of this context abstraction. It's the same you can say for the detail abstraction that is mainly based on some kind of implementational issues and using the hiding principle. So in this case we come now to some concepts how we can compose a model. There's some principles. One is of course that your model construction can be based on decomposition, on abstraction and information hiding, on maybe component and modularity, maybe on extensible, maybe in an onion or shell approach. You have maybe some integration architectures or some hierarchical relationships. We come later, and there's the issue of model suites for both hierarchical and vertical, let's say, model construction methods. The main goal for model management is, of course, to manage the model complexity, to improve the quality, to facilitate maybe a systematic reuse of the given model for another application case, but with the same function. That means in this case we have a systematic reuse for resolving common modeling challenges maybe. Okay, then we have a number of construction principles. First of all is modularization. Modularization is nothing else as you separate different things of concerns into independent components, and in this case maybe the components can be even used in an organized fashion, or at least you can say, okay, fine, one component is more specific than another component. For this reason you can use some kind of parameterization. It is typically based on some kind of information principles, hiding principles, which have been introduced in computer science by Parnas. Or you can use maybe substitutability principles introduced by Liskov that relate the objects of a specialized class to the objects in a more general class by stating all methods or principles from the general class can of course be somehow used by the more specialized as long as they're not overwritten. You have some interfaces, some applications, some views, some hierarchies. That is one thing. I will come back to the component in a minute again. You have abstraction, and another thing, when you decompose, you have a coupling facility. The coupling facility should based on some coherence of concepts that you are using in your model. That means in this case you can say, okay, fine, you have an enforcement that is lazy or that is maybe easy to go. You might have a coupling that is tight or close. No, tight or loose, yeah. Or you might have some integration or collaboration of components. To componentization I will come back in chapter 9 when we are talking about model suites. Before that I want, however, to relate all this to component-based model specification. You can do it now on the service model I have been introducing in this lecture as an example. You say, okay, fine, a component is nothing else as you have a name, you have exported services, you have imported services, and you might have some usage constraints. The functions of a component can be, in this case, separated into export functions, import functions, constraint maintenance functions, and maybe you have also some kind of functions for mapping the names to proper names that can be used in a component set. And then in this case you can say, okay, fine, you can have views of the component, maybe of the component structure, of the collection of components as well, based on some kind of architecture that is nothing else as a model how these components are interrelated. Maybe you have some kind of infrastructure architecture view, and maybe you have some technical architecture view that is nothing else as a classical quasar architecture introduced in the 90s by Siedersleben. In this case, you can say, okay, fine, a service is somehow consisting of an export service and or an import service, and you have maybe for the service a type and a mode. You have a service resource type, you have components, a quality of service you can specify, and again you have the same functions of the service. In this case, you can say, okay, fine, with this kind of specification, I can say for exported services, they are exported by component, maybe to some kind of architectural connected components. And you have, of course, import services with a corresponding signature. All of this can be based on the abstract state machines specification approach, and for this reason you can have now this very general, let's say, mappings. And the interfaces can be also specified this way. So you can say, okay, fine, I provide services, I require services. Maybe services should meet our expectations, our constraints, and then you have a satisfies constraint specification, and you have, of course, a connector based somehow collaboration of components, and for this reason you can say, okay, fine, a connector imports something and exports something, imports maybe services and exports services. So you have a general framework for how the model components can be interrelated. Okay, and then in this case you have nothing else as you can now say, okay, fine, you have now maybe restrictions you can specify by axioms. For the services, the interrelationship, their mapping of the import and export. Maybe you have acyclic connections or cyclic connections, as long as you can handle those, it is also allowed. And you have, of course, let's say something like each imported service is connected with at most one exported service through a connector or an abstract connector. That means in this case you have nothing else as you use in electrical circuits thinking. You have a plug, and the plug could be an export plug or an import plug, and the export plug and the input plug should somehow correspond to each other. What you export can be more than what you import, but the import plug should have at least a correspondence to what is exported. So one final remark. What you have in this case now, if you use some kind of composition architectures, then you say, okay, fine, I have now something like I use my models in a certain application according to the functions in a componentized, maybe somehow interrelated components, maybe somehow orthogonal components, maybe somehow even independent components way, so that you can build those things in a proper way. A typical application of this approach is you have some original system, an origin, you have maybe some replacement system you want to have at a later stage, and you have now somebody who experiments with some kind of mappings between the original system and the replacement system. This is, for instance, what our people in our technical faculty are using for somehow supporting people who drive in a car, let's say in a Caprio, in a heavy driving situation and want to have a telephone call through the classical or the modern telephone connection of the car. In this case, of course, the noise around is somehow really annoying and somehow making a lot of random noise for you. In reality, however, you want now to restrict this random noise in such a way that you can make a telephone call. Then in this case you have nothing else as a replacement system that replaces now somehow this behavior of the noises in such a way that you don't have, let's say, or you don't recognize this noise, and you have only the speeches given by the mobile phone, and you can also speak being in this noise to your partner. That would be a very nice, let's say, application for a composed system. making experiments and simulating, in this case, by mathematical methods, by computer-aided analysis, and etc., how it would be handleable. In the second part of this lecture now, I will come back to our 9 tuple for specification of the model being. I will put it into a compliance framework, and I will talk a bit more on how to inherit whatever has been already developed in a proper way in the generics part. Thank you.